Have you ever wondered why your local news channel or the weather app on your phone can't seem to accurately predict the weather more than a few days out? I'm Dr. Dick, an unlicensed doctor, scientist, and meteorologist, and today in this presentation, we're going to take a deep dive into why this is, and we're going to explore some ideas and theories that may just lead you down a Wikipedia or YouTube rabbit hole.
And curiosity often leads to trouble.
Now, before we get into these ideas, I want to share a little bit about my history. If you haven't seen the movie Good Morning Vietnam, pause the video right now and go give it a watch.
Good morning, Vietnam!
If you have seen it, you'll know that Robin Williams plays a radio DJ in the Air Force during Vietnam. Now, I filled a similar role playing a radio DJ. Well, I was actually a radio DJ in Sicily a couple years back while I was in the Navy. There's nothing quite like talking to thousands of people on the radio. One of the most unique jobs I've ever had. Now, you're probably wondering, Dr. Dick, why are you telling us about this? How is this relevant? And if you would just hold your horses, I'll explain.
And that's the way the news goes.
You're listening to the Smooth Grooves on 105.9 The Eagle. Here's your local happenings and the weather with Captain Fantastic.
You see, once an hour, I would give the weather, the weekly weather forecast, and the current exchange rates. And I noticed that after about a year of this, that the weekly weather forecast, it wasn't always right. And this led me to wonder why this was. But naturally, being in Sicily, there was just so much adventure to be had and so much beauty to be seen that I kind of forgot about it until I enrolled in my class Sacred Geometry, which is actually what this presentation's for. In that class, we learned about this guy named Edward Lorenz. Ed is what I would consider a pretty smart dude. He got his bachelor's degree in mathematics at Dartmouth, then a master's degree in mathematics from Harvard. A few years after graduation, Ed served as a weather forecaster in the U.S. Army Air Corps. That's the precursor to the Air Force. He served from 1942 to 1946. He earned an additional master's and then doctoral degree in meteorology from MIT, finishing up in 1948. He then spent the rest of his career at MIT. It's pretty cool, I would say. Needless to say, he was a nerd. And I can say that because I'm one myself. In 1961, Ed was working on simulating weather patterns using this monstrosity. One of the most advanced computers at the time, this technology allowed Ed to simulate weather patterns and model up to 12 different variables at once. During the winter of 1961, Ed wanted to examine a sequence at greater length, or rather, re-examine a sequence. Due to the relatively slow speeds of computers during this time, if you can imagine that, Ed decided to take a shortcut and start midway through. At the time, the computer's memory stored 6 decimal places. The original sequence number was 0.506127. When re-entering the numbers, Ed only entered 0.506, thinking that the difference would be inconsequential and save time.
Erroneous! Erroneous! Erroneous on both counts!
When looking at the results an hour later, he realized that this was not the case. He articulates perfectly what happened in his 1963 paper titled Deterministic Non-Periodic Flow. Two states differing by imperceptible amounts may eventually evolve into two considerably different states. If, then, there is any error whatsoever in observing the present state, and in any real system such errors seem inevitable, an acceptable prediction of an instantaneous state in the distant future may well be impossible. In view of the inevitable inaccuracy and incompleteness of weather observations, precise, very long-range forecasting would seem to be non-existent. And that, folks, is why we cannot accurately predict the weather. Mic drop. But not really, because it's too expensive. Now, that same 1963 paper has led to a paradigm shift that has permeated much of science. An article in Physics Today articulates this shift perfectly. Author Tim Palmer says, Many biological and physical systems display behavior that is complex or apparently random, but the equations that describe the evolution of those systems are themselves not necessarily either highly complex or random. Instead, the behavior may suggest the fractally dimensioned geometry of the low-dimensional strange attractor. In layman's terms, many of the events that we view as random and complex are, in fact, not. This can be represented geometrically if the variable is 2 or 3 dimensional. Strange attractors that are chaotic exhibit sensitive dependence on initial conditions. That's kind of important. A tangible version of this can be demonstrated with a double pendulum. I built this rudimentary example using ABS plastic, ball bearings, and a few bolts. The dynamic behavior of this double pendulum has a strong sensitivity on initial conditions. You can see an example of how this plays out in these photos. These were all long exposure photos, which means the shutter was opened for an extended period of time, in this case 15 to 30 seconds, and I attached an LED light to this, racked the pendulum back, and let it go. These photos are what happens when you let that pendulum go. Similarly, this next video shows this, but it is important to address the fact that this representation is taking place in what would be considered phase space, where all possible states of a physical system are represented. 2 arbitrarily initial points on the attractor, after numbers of iterations, will lead to points that are both arbitrarily far apart and arbitrarily close together. This leads to local instability, but at the same time, global stability. This is the reason why it's so hard to predict weather. Yes, we can understand and plot what is happening. Still, the sensitive dependence on initial conditions makes it nearly impossible to predict exactly what will happen because we simply cannot predict minute details, like the flapping of a butterfly's wings. The butterfly effect is part and parcel of chaos theory, otherwise known as chaotic amplification. As Tim Palmer puts it, this is the idea that arbitrarily small-scale disturbances can influence large-scale disturbances. This idea was first introduced by Ed in his 1969 paper, 3 Approaches to Atmospheric Predictability, where he uses the metaphor of a seagull flapping its wings. It wasn't until a 1972 conference that the idea of the butterfly was introduced. It was actually this guy who chose the title of Ed's talk. Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? It makes sense that the enigma that is the butterfly effect, being both so seemingly simple yet complex, is so prevalent in movies, TV shows, and writing. This brings me to the final point and question of this video presentation. Is there an event in your life that has spawned a series of events that have changed the direction of your life or made an unexpected impact? Have you seen or felt the flap of the butterfly's wings? I know I have.
It's that real shit, yo.
Butterfly in the sky.
Come on!
I can go twice as high.
Let's get it on.
Take a look.
Oh, hey, it's me again. I'm just giving a little caveat at the end of this video. I'm just a student, and all of this stuff would be considered research. This is all other people's information, all other people's ideas, so just take that with a grain of salt. Everything that you heard in this video was as accurate as I could make it, but that doesn't mean that it's accurate. I may have made some mistakes, so be sure to do your own homework. Thanks for watching. It does this. I'll probably cut that, but I may leave it in.